Yes, any questions before we start? Now, if you remember, the last thing we did last week was we were discussing the separation of variables. So what we did in separation of variables was we are trying to solve the Laplace's equation. And by looking at our boundaries, I mean, we would like to choose a coordinate system, whether it's the Cartesian or spherical or cylindrical, in which the boundary we can represent in a simple manner. For example, if you have rectangular objects, like if you remember, we had studied this problem of two infinite planes, and the upper part and the lower part were both grounded. And this part was given a potential V0y, x is the horizontal axis, y is the vertical axis. And to solve this problem, what we did was we assumed that phi was a product of two functions, one depending on x, the other depending on y. And we determined what the differential equation, what kind of differential equations these functions x and y should satisfy, and then what are the possible choices for these functions x and y. And if you remember, we had seen that y should have been in the form of some constants, sine n pi over a, y, a depends on n, and then x turned out to be some coefficient e to power minus n pi over a x plus c n e to power plus n pi over a x. And then we try to impose the boundary conditions, such as this function y should be 0. Y should be 0 when y is equal to 0, or it should be 0 when y is equal to a, to make sure that the lower plate and the upper plate was grounded. So that is in fact how we obtain this sign without any additional term. And also when x goes to infinity, this function x should be 0, because away from this source of the potential, there cannot be any potential. Everything is 0. Yes?
I forgot my homework in the library. Can I bring it in the break?
In the break, sure. Bring it in the break. And then we had this boundary also, which basically told us that this term should be absent because this term just diverges at when x becomes very large. It becomes very large instead of going to 0. So c should have been 0. Now, of course, there's still one more boundary condition. We have the boundary at x is equal to 0. When x is equal to 0, y, this function, when x is equal to 0, phi should be equal to this function. But we cannot impose that boundary on functions of this form. But what we did was, you see, there is this parameter n which is not fixed. It can take any value. And in fact, for every possible value of n, we have a solution of the Laplace's equation satisfying these boundary conditions. So what we did was, if you just take any superposition of these functions, phi should be equal to Cn sine of n pi over a y times e to power minus n pi over a y. This sum with some coefficient Cn satisfies the Laplace's equation, satisfies these boundary conditions. And then the question was, is it possible to choose these Cn's such that this function is equal to V0y on the vertical boundary? And we said, okay, fine, we know the Fourier theorem. It says that any function, in this case V0y, can be written as a sine series. And we determined what Cn's were. So we have now we have a function. Once we determine this Cn, we have a function that satisfies the Laplace's equation and that satisfies all our boundary conditions. So basically we have the solution, because uniqueness theorem tells us that there is a single one. So this is a solution, so it is the only one. Another example we looked were when we have spherical objects, like when you have a sphere. Basically we did the same thing. Well, in this case, we considered a simple problem which didn't depend on the z coordinate. But the basic idea would be the same even when you have a function that, when you have a problem that will depend on the z coordinate, the only difference would be just multiply this with a function that also depends on z. It will just make it technically a bit more complicated, but the principles are always the same. The principles are always the same even in spherical coordinates. And again, we assumed a simple problem where the potential depended only on r and theta. For example, this can be, we had already studied the problem of a uniform sphere in the presence of a single charge. If you choose your z-axis to go from the center of the sphere to the point towards your charge, then nothing depends on rotations around the z-axis, nothing changes. So this problem doesn't depend on the phi coordinate. Or we will be studying today for the example of a sphere in a uniform external electric field. If you again choose your coordinate z-axis to be along the electric field, nothing depends on rotations around the electric field, around the z-axis, so the potential should be independent of phi. Now, in this case, we again assume this to be a function of r multiplied with a function of theta, and we call that function ze, for a shorthand for Zeynep. And then we had found what these functions are supposed to be, and we had seen that this radial part has to have this form. And this angular part has to be basically a function, a polynomial of cosine theta. Now, what are these polynomials? Well, we don't really need to know a lot about those polynomials. It will be enough if you just remember a couple of them. When L is equal to 0, they are just 1. When L is equal to 1, they are just x. When they are 2, they are just 1 over 2, 3x squared minus 1, etc. They are tabulated, they are formulas to obtain their expressions, etc. I mean, most of the time we will basically need just a couple of them. They're just polynomials. For us, the important thing is that one thing, they are complete, in the sense that if you have any function of theta, which is finite everywhere, you can write it in terms of Legendre polynomials of cosine theta. That is what we need. And furthermore, if you just multiply two of them, multiply by sine, and integrate over theta from 0 to pi, you get 2 over 2L plus 1 Kronecker delta LL prime. Well, this just tells me that if L and L prime are different, then they are, the integral is 0. If they are the same, then we have a normalization constant, let's say, which is a function of L. So this is where we had left, in a sense. Now, any questions?
We don't need to know what the Rodriguez formula is, right?
No. I mean, if you will need it, I will give it to you and ask you to use it. Now, let's do a couple of examples over here. Sorry, before continuing. Okay, we have these Legendre polynomials, we have this radial function, and the most general solution in spherical coordinates of a potential that doesn't depend on the phi coordinate is just a superposition of these AL R to the L plus BL 1 over R to the L plus 1. Summed over L from 0 to infinity. Of course, there is also this PL of cosine theta. This is the most general form. So let's do an example. Let's start with the simplest thing that we can think of. Let's assume we have a spherical conductor such that the surface is at the potential V0. So we kind of connect it to a battery or something like that, such that the potential of the surface of the sphere should be V0. Now, in such type of problems, your boundary already, well, you see, the one thing over here is we had discussed the solutions of the Laplace's equation, but to keep the boundary at V0, this conductor has to be charged. So there are some charges. So the potential satisfies the Poisson equation. If you just, we have to solve not the Laplace equation, but Poisson's equation. But you see, we can do a trick. This is a conductor. So we know that the charges are on the surface. Since the charges are on the surface, inside the conductor, there are no charges. So inside the conductor, the potential satisfies the Laplace's equation. And since the potential satisfies the Laplace's equation inside, we know the general solution. Let's call it phi in, meaning inside our surface. This should be equal to AL R to the L plus BL 1 over R to the L plus 1 times PL of cosine theta. Let me also put the label in on top of AL and BL. Well, what else do we know? We know that at R is equal to 0, the potential should be finite. So because the potential is basically finite, wherever it satisfies the Laplace equation, the maximum is only at the boundary, and at the boundary it's V0, so it has to be finite. Since it is finite, at R is equal to 0, this term cannot appear in this expansion because this term just diverges. So BL inside should be 0. So phi in will have this general form. Inside. Now let's look at the outside. Again, this is the general form. But we also know that at infinity, the potential has to go to 0. When we set R goes to infinity, all of these terms, they go to 0 because due to this 1 over R to the L plus 1, L is from 0 to infinity, so this is always a positive exponent, so it goes to 0. But these terms diverge. Well, if L is non-zero, they diverge. If L is 0, they become a constant. But at infinity, the potential is 0, so all of these terms should be 0. If AL out is non-zero, we cannot satisfy the boundary at R is equal to infinity. So now we have the general solutions both inside and outside our sphere. Now we have to impose some boundary conditions on the surface of the sphere. One property we know is that on the surface the potential should be continuous and it should be equal to V0. So V0 should be equal to L from 0 to infinity, AL in R to the L, PL of cosine theta. And it should also be equal to, from L is equal to 0 to infinity, BL out, 1 over R to the power L plus 1, PL of cosine theta. Out. Okay, so here. So this is how the potential looks outside my sphere. And I said that if r go to infinity, that is, we are at very far away distances from the sphere, the potential is 0.
Yes, but why the potential is not phi out?
Sorry, that is phi out. Because when I'm at r equal to infinity, that is I'm outside the sphere. Well, I will jump a couple of steps here. You see, if L is non-zero, then this is a function of theta. It changes with theta, these terms. But the left-hand side is independent of theta. So it basically tells me that I have to set everything here, AL in and BL out, to 0 if L is non-zero. So basically, in these sums, we have just a single term. So the L equal to 0 terms, V0 is equal to, well, let's rewrite the first term. Only the L equal to 0 survives, so we have A0 in. This is where I am actually using P0 of cosine theta is equal to 1. So that's why I know that it is 1, it is independent of theta. So in the first line over here, the L equal to 0 term is V0 equals to A0 in. And in the second line, there's only the L equal to 1 term, L equal to 0 term again. V0 is equal to B0 out times 1 over R. So this allows me to determine what B0 out is. This is equal to R times V0. Now we can write down the potential. Everywhere, the potential as a function of R and theta, this is equal to, inside meaning small r is less than capital R. You see, this is the general expansion in the first line. Only the L equal to 0 term is non-zero, and L equal to 0 terms is A0. But A0, we had just determined that it is supposed to be V0. And when we go out, phi out is this line over here. Now, of course, this is for a general R. Now, let me just show the actual expression for phi out. Okay, the phi out is that line over there, the first line. We already had said that AL should be 0. There is only the BL terms. And among the BL terms, only the L equal to 0 term survives. And L is equal to 0 term is just B0 divided by R to the L plus R. B0 times R. And B0 is nothing but V0 times R over R. Sorry, small r. Well, this is actually the solution that we already know. If you have a sphere, if it is charged, we know that the charge will be distributed uniformly on the surface, and outside it just acts like a point charge, hence the potential drops as 1 over R. Inside there is no electric field, so the potential should be 0. So it's just, we have solved a question whose answer we already know, and the solution is consistent.
But here the potential inside the sphere is not 0, it's V0.
It doesn't, now, it doesn't have to be 0. The electric field is 0. So the potential is constant inside. So if you have this uniform conducting sphere, the charge is on the surface. Inside, the electric field is 0, so the potential is 0, is constant, sorry, non-zero, but constant. That is what we find. Outside, it just acts like a point charge whose potential drops with as 1 over r.
Hocam, şimdi burada outside'a baktık ya. Hani şöyle burada herhangi bir hacime mi baktık yoksa?
Any point outside my sphere, some point.
Peki diyelim ki kürenin içinde de yükler var. Ben hiç pozisyonla falan uğraşmak istemiyorum. Burada bir şey yapmak istiyorum, maklas yapmak istiyorum. Öyle bir şey mümkün mü?
Sure. But how do you impose the boundary conditions? How do you match? Let's do another example. This time, let's try to solve a problem whose answer we do not know. Let's just assume we have this sphere, again, conducting sphere. And let's assume that we put this in a uniform external electric field. So we have this, at least far away from the conducting sphere, the electric field is uniform. Of course, the electric field will be modified because this external electric field will move the charges in my conductor. Some charges will go to one side, the negative charges, positive side charges will go to the other side, in such a way that the electric field lines will fall perpendicular to my sphere. This is more or less how it will look. The electric field line. So the question is, how can we find this electric field line? Well, we don't need to worry about what the electric field inside our sphere is because we already know that it is 0. The electric field line inside the sphere is 0. We can use spherical coordinates because that is easy to impose the boundary condition. And we can choose, the easiest thing would be to choose the z-axis to be in the direction of the electric field line, such that if you rotate our system around the z-axis, nothing changes. Well, rotating around the z-axis changes phi coordinate, so nothing should change as you change the phi coordinates of your point, so the potential doesn't depend on phi. But we already know the general expression for the potential in such a case. This is equal to L from 0 to infinity, AL times R to the power L plus BL times 1 over R to the power L plus 1 times PL of cosine theta. This is the general form. Now we have to find the boundary conditions. So let's say this is our origin, this is the radius. So whenever we are talking about the potential, first we have to determine where should we put the 0 of our potential. Most of the time it's at infinity. But you see now we have electric fields that go to infinity. So the potential difference between, let's say, this point and the point at infinity will be infinite. So we cannot really set the potential at infinity to 0. So we have to choose some other point to set the 0 of the potential.
Can you repeat why we can't set the potential?
You see, let's look at this one. Let's calculate the potential difference between this point over here and that point in that infinity. E times infinity. The potential difference is infinite. So if we set the potential at infinity to be 0, then we don't need to do much work. All the potential here is infinite. And it won't be easy to talk about their derivatives, etc. So we should better take another point to set the 0 of our potential. So where would you like to choose that? At the center. Fine, that's great. At the center we can set the potential to be 0, but that also means that on the sphere, on the surface of the sphere, the potential is 0. because inside the conductor there are no electric fields. So that is one of our boundary conditions. R is equal to capital R theta, this should be equal to 0. This is one boundary. Well, this boundary only doesn't cover our volume, because our volume extends up to infinity. We have another boundary at infinity. So we should also set what the value of the potential should be at infinity, or close to infinity, let's say. Now, very far away, we know the electric field. So what is the potential that gives this electric field? What is the potential that would give me such an electric field? Minus E0 minus E0 z, for example. So if you take the gradient of minus E0 z, you end up E0 in the z direction. That is, this is one possible potential that would correspond to our uniform electric field at very far away distances. This is the potential, let me call it phi E. E0. You see, the potential difference, we had defined that minus E dot dz, dl. So this is equal to minus, if E is constant, E0 times delta L. Okay, E0 is constant, but the potential difference is not constant. If potential is constant, you see, electric field is the gradient of the potential. Derivative of the potential gives me the electric field. If the potential is constant, that just means that its derivatives are 0. Now, this is my other boundary condition. Phi, when R goes to infinity, R can go to infinity in any direction. Because if I am very far away from the sphere, I should recover my uniform electric field. The sphere over here will not influence the electric field over there. This should be equal to minus E0z plus some possible constant. Let me just choose it to be 0. Which I can also write as minus E0 R times cosine theta. This is equal to minus E0 R times P1 cosine theta. Because P1 of cosine theta is nothing but cosine theta. And now I know my boundary conditions. I have one boundary at small r is equal to the radius of my sphere. I have another boundary when small r is very large. It approaches infinity. Let us impose those boundary conditions now. Let us start with this boundary condition. So, limit as r goes to infinity of L is equal to 0 to infinity AL R to the L plus BL 1 over R to the L plus 1 PL of cosine theta. I know that this should be equal to minus E0 R P1 of cosine theta. You see, when R goes to infinity, these terms, they just go to 0. Only these terms remain. But you see on the right-hand side, we have a function that increases linearly with R. So on the left-hand side, we should also have a function that increases linearly with r. So that is the L is equal to 0 term. L is equal to 1 term. And also, if you look at the angular dependence, on the right-hand side, we have the angular dependence given by P1 of cosine theta. On the right-hand side, we should have an angular dependence that is given by P1 of cosine theta. That also tells me that it should be L is equal to 1. So this basically tells me that AL is equal to 0 if L is larger than or equal to 2. This boundary. And A1 is equal to minus E0. It doesn't really tell me anything about A0.
Hocam biz E0'yu bulmaya çalışıyoruz. E0'yu bulmaya çalışıyoruz.
No, we want to find phi everywhere. We are already given E0. So you take two parallel plates, very large, create a uniform electric field. Inside you put this sphere. And you ask, what is the electric field near this sphere? So that's the question we are trying to answer. We already know what E0 is. But what we are trying to find is phi. And the electric field everywhere. E0, okay, we are applying this electric field E0, but this conductor modifies our electric field. So what is the new electric field? So just imposing one of these boundary conditions, we are left with a potential, which is A0. We don't know what that is yet. Plus A1 is minus E0 times R times P1 of cosine theta. Plus L from 0 to infinity, we cannot say yet anything about BL. So this function satisfies our Laplace equation, and it corresponds to this potential corresponds to a uniform electric field at distances very far away from our sphere. Now there is one more boundary condition we should impose, that when small r is equal to the radius of the sphere, this should be 0. So phi, when r is equal to capital R, whatever the value of theta is, this should be 0. So this gives me A0 minus E0, P1 of cosine theta, plus sum over L from 0 to infinity, BL 1 over R to the L plus 1. Here we have R, PL of cosine theta. This should be equal to 0, whatever the value of theta is. So what is the theta independent term on the left-hand side? A0, it doesn't depend on theta. What else?
BL.
L is equal to 0 term. B0 over R to the power L plus 1. This should be equal to 0. Well, this is the coefficient of P0. What is the coefficient of P1 on the left-hand side and also on the right-hand side? P1 cosine theta. On the left-hand side, the coefficient is minus E0R plus B1, 1 over R squared. This is the coefficient of P1 cosine theta on the left-hand side. On the right-hand side, What is the coefficient of P1 cosine theta? 0. There is no P1 on the right-hand side. Okay, what is the coefficient of PL cosine theta on the left-hand side for L larger than 1? On the left-hand side, it is not 0. It should be 0. This should be equal to 0 for L larger than or equal to 2. Do you agree?
Let me ask this. If L, I mean, in A0 plus B0 over R to the L plus 1, if L is 0, why do you have L in the
We don't. Other questions? So we just picked up the most general solution in spherical coordinates. We determined our boundary conditions, and now we are imposing our boundary conditions. So let's see, B0 is equal to R times A0. B1 is equal to E0 times R cubed. And BL is equal to 0 for L larger than 1. Now we had already determined most of the A coefficients. Now we also know the B coefficients. So we know the solution. You see, this was our general solution, subject to our boundary conditions at infinity. So this is equal to A0 minus E0 or P1 cosine theta plus, well, B0 is R times A0. Sorry, I have a minus sign over here. Minus R times A0 times 1 over R to the 1 over R times P0 is just 1. Plus B1 is E0 R cubed 1 over R squared P1 of cosine theta. Or let's combine them a bit. Phi is equal to A0, 1 minus capital R over small r, minus E0 times P1 cosine theta times R times 1 minus R cubed over small r cubed. We are almost done. Almost. Well, when small r goes to 0, when small r goes to capital R, this is 0, so we satisfy the boundary at r is equal to to the radius of the sphere. When r goes to infinity, then phi is equal to, well, we had made a small mistake over there. Phi, when r goes to infinity, is now A0 minus E1 r P1 cosine theta. And we had, no, this is E0. And this has to be equal to minus E0 r P1 cosine theta. So that was one mistake we did. So we can trivially set A0 is equal to 0. Well, the mistake we basically had, what was the mistake we did? At one point, my argument was not strictly correct.
Merkezi sıfırlıyor.
Well, I'm far away from the center. True. Or is it? Does phi go to infinity everywhere? Remember, PL of cosine theta is cosine theta. So if cosine theta is 0, the potential is finite. And if cosine theta is 0, the potential should be 0. But our solution gives A0. So A0 has to be 0. So that was kind of our mistake was saying that when R diverges, when R goes to infinity, the potential, these terms diverge, so we can just ignore a constant term. It's not really true because there is a point, there is a plane, on the Z plane, the potential is 0. It should go to 0, it doesn't diverge on the Z plane. So that's why A0 is 0, and hence we determine the potential uniquely. This is equal to minus E0 R cosine theta, 1 minus radius cubed divided by R cubed. Now this satisfies the Laplace's equation, and it satisfies the boundary conditions. Now that we have the potential, what about the surface charge density? Okay, if you remember, when we were discussing the problem at first, we said, okay, if you put it in a uniform electric field, negative charges will move on this side, the positive charges will move on the other side, so there will be a surface charge density on the surface of my sphere. So what is the surface charge density? Well, we know the potential. From the potential, we can calculate the electric field. And if you remember, the discontinuity in the electric field across a surface is proportional to the surface charge density. Now, we already know that since we are looking at a conductor, on the surface of the conductor, the electric field should be in the radial direction. Or in fact, let's calculate the electric field. We know the potential, the electric field is minus the gradient of the electric field, the potential. You just need to pick up and look at the expression for the gradient in spherical coordinates. So this is equal to minus del phi by del r. In the radial direction, minus 1 over r del phi by del theta. In the theta direction, which is equal to, if you take the derivative with respect to r, it is minus E0 cosine theta 1 plus twice r cubed divided by small r cubed. This is in the radial direction. And minus, now this is plus. There is a minus over here, there is a minus over there, so that makes a plus E0 cosine theta, 1 plus 2r cubed over r cubed. In the r hat direction, if you take the derivative with respect to theta, you get a minus E0 r sine theta, 1 minus r cubed over small r cubed in the theta hat direction. Now, you see this minus cancels this minus. That makes a plus. When you take the derivative of cosine, you get an additional minus. And now when you set small r goes to infinity,
Hocam şu değil. 3 bölü r üzeri 4 olması gerekiyor.
so there is a 1 over r. So this r is absent. This one over here. You see, you multiply r with this, you have the r. If you take the derivative, that is 1. Then you have minus a radius cubed divided by r squared. If you take the derivative of r squared, you get a minus 2 over r cubed. So minus makes plus 2 over r cubed. Well, you can just double check your answer. Okay, first of all, on the surface of the sphere, is it perpendicular to the surface? Well, on the surface, small r is equal to the capital R, so this term is 0. So there is no theta hat component. The electric field is in the radial direction. So that is good. The second thing, away from the sphere, the electric field has to be uniform. If you set r goes to infinity, r becomes very large. This term just goes to 0. This term just goes to 0. You have E0 cosine theta in the r hat direction minus sine theta in the theta hat direction. Is it a uniform? Is it a constant vector field? So you see, we are checking this one. Electric field when r is very large. This is equal to E0 cosine theta in the r hat direction minus sine theta in the theta hat direction. And our starting point was that the electric field very far away from the sphere should be uniform. So this should be equal to E0 z hat. Is it true? Well, you see, as you change theta, cosine theta changes. So it doesn't seem to be a constant vector, this one. So did we do something wrong?
Şunu kartezyen çevirince zaten z eti ver.
True. If you just convert this to Cartesian coordinates and Cartesian vectors, this combination is the z hat vector. So it's just the z hat vector in spherical coordinates. So kind of the solution, the potential that we found, that is the electric field corresponding to the potential that we found, does satisfy what we expected from the electric field. It had to be perpendicular to the surface. It had to be uniform very far away from the sphere. Now we can determine the charge density on the surface. And if you remember, the charge density on the surface was this one. You calculate the electric field outside, you subtract the electric field inside. This has to be equal to epsilon sigma over epsilon 0 in the direction pointing from inside out. Now this is our sphere. At this point, at an arbitrary point, this is the n hat vector. So this is inside the sphere, outside the sphere. Now what is the electric field inside? Zero. It's a conductor. The electric field outside, meaning just outside the surface, not far away, just we have the surface on this side of the surface and then on the other side of the surface. Well, the outside surface, this is our electric field, the first line over there, that is the electric field at any point outside my sphere. On the surface, I just need to put small r is equal to capital R, the second term is 0, and the first term just gives me 3E0 cosine theta. In the radial direction, just look at their difference. 3E0 cosine theta. This is equal to sigma over epsilon 0. So n hat is nothing but the radial vector. So we know what sigma is. This was the direction of E0. We had already suspected that this side, the left-hand side, should be negatively charged, the right-hand side should be positively charged. Remember, this is my z-axis. So from theta is equal to 0, this along the z-axis, to theta is equal to pi over 2, cosine theta is positive, so the charge density is positive. From theta is equal to pi over 2 to theta is equal to minus pi, that is this side, which we expected to be negatively charged, cosine theta is negative. And the total charge is 0. Now let me reverse this problem a bit. Now any questions on this problem?
Elektrik alanla alakalı ifade değil çocuklar. Burada içeriye bakmaya çalıştığımızda ara sıfır verdiğimizde ne oluyor?
Now you see, we started from assuming that we are looking at only outside the sphere. So this electric field is valid only outside the sphere. So I cannot put R is equal to 0. This is not true inside my sphere. We already started by saying that inside the sphere the electric field is 0, or the potential is constant. So this is valid only if small r is larger than capital R. When small r is smaller than capital R, the electric field is 0.
Aşağıda üçü nasıl bulduk hocam outside?
So outside, what I did was, here I just replaced small r is equal to capital R. So this is just 1. 1 plus 2, 3.
Charge integralden cos thetadan dolayı
0. Yes.
cos theta olmasaydı eğer sıfır değil.
Well, depends. If it was cosine cubed theta, it would still be 0. Now, before you go for a break, let's just do one more example. This will be a short one. This is the question. You have a sphere. On the surface of the sphere, there is a charge distribution. So let's say this is our z-axis. On the surface, there is a charge density which depends only on theta. And sigma of theta is equal to 3 epsilon 0 E0 cosine theta. What is the electric field inside? This is not a conductor. There is no external electric field. There is only the surface charge density on the surface of the sphere. And so it just gives us positive charges on this side, negative charges on the other side. So inside there's an electric field in this direction. It need not be uniform, but so what is this electric field? So this is kind of the first hint. It's in the minus z direction. This is the electric field inside. Why? Well, we just pick up from the previous question. You see, in the previous question, the electric field inside the conductor is 0, basically because there is this external electric field that we apply, plus the electric field created by these charges. That sum is 0. Here, the surface charge density is basically the same as the previous problem. So the electric field that this charge density creates should be exactly equal to minus the external electric field, so that they cancel inside the sphere. So it is uniform. It's a uniform electric field in the opposite, in the minus z direction. Okay, let's give a break, a 10-minute break. You can ask your question either during the break or after the break.